Here's a question. How many people do you need in a room for a 50% chance that two of them share a birthday? Before you answer, your gut is probably saying something between 100 and 183. Half of 365. The actual answer is 23. And when you see the proof, it will permanently change how you think about probability. The answer is 23. Let's prove it together, step by step. There are 365 days in a year. Think of each day as a dot. When a person walks into the room, their birthday lands on one of these dots at random. The question we're asking is, what are the chances that at least two people land on the same dot? This seems like a question about one person against 365 options. But it isn't, and that's exactly why our intuition fails us. Here's the mistake your brain makes. It asks, what are the chances my birthday matches someone else's? 1 in 365. About 0.3%. So you need around 300 people for 50%. Right? Wrong. Completely wrong. Because that's not what we're asking. We're not asking about your birthday specifically. We're asking whether any two people in the room share a birthday. That's a totally different question. And the answer is shockingly different. The right way to think about it. We need at least one pair of people whose birthdays match. So the question is really about pairs, not individuals. Here's the key insight. With n people in a room, the number of unique pairs is n times n minus 1. Divided by 2. 10 people, 45 pairs. 20 people, 190 pairs. 23 people, 253 pairs. 30 people, 435 pairs. Each of these pairs has an independent chance of sharing a birthday. 253 pairs. Each with a small but real chance of matching. That's why the probability climbs so fast. The math is working behind the scenes. Let's build the probability mathematically. The cleanest approach is to calculate the probability of no match. Then subtract from 1. Person 1 enters the room. No constraint. They can have any birthday. Probability of no match. 365 out of 360. Person 2 enters. They must avoid the one birthday already taken. Probability of no match so far. 364 over 365. Person 3 must avoid 2 birthdays. 363 over 365. Each new person multiplies the chance of no match by a slightly smaller fraction. Slowly at first, then the product. Look at this curve. As people enter the room, the probability of a match climbs slowly at first, then it accelerates. At 23 people, we cross the 50% line. Person 23 multiplies by 343 over 365. The combined probability of no match drops to 49.3%. Which means the probability of at least one match is 50.7%. 23 people. That's all it takes. A 50% chance that two of them share a birthday. And it only gets faster from here. With 57 people in the room, the probability crosses 99%. In a group of 57, it's almost certain someone shares a birthday. The birthday paradox is just one example of how badly our brains handle probability. The Monty Hall problem shows that switching doors doubles your win rate. The gambler's fallacy fools people into thinking past coin flips